Good morning there, everyone. We are going to begin our videos on sequences and series. And I think you'll find at least the first couple sections here pretty easy and maybe even interesting if we're lucky here. So we have arithmetic and geometric sequences. And in arithmetic, you're going to find out here, hopefully, very shortly, that arithmetic is very similar to linear functions, which you guys know a great deal about. And geometric is very similar to our exponential functions, which again you know a great deal about, but not so sure you enjoy them as much as linear functions. Linear is easy. Exponential would make you think a little bit. They should be the more enjoyable ones. Thought-provoking is always more fun. So we're going to begin by defining these. Arithmetic, as I just mentioned above, is very similar to linear. And you'll see the difference here towards the end of this video here. But an arithmetic sequence, by definition, is a sequence of terms that have a common difference. So common difference is what we are looking at here. A sequence of terms with a common difference. For example, 3, 6, 9, 12, 15, ... They have a common difference. In this case, the common difference is simply 3. D equals 3. Some notation to get used to. This term right here, the beginning one, is not the intercept or anything like that. It's the first term. T sub 1 equals 3. T sub 2 equals 6. T sub 3 equals 9. So on and so forth. T4 is 12 and T5 is 15. Okay, so you can clearly see that if I look at consecutive terms, 6 minus 3, 3. 12 minus 9, 3. 15 minus 12, 3. I will always get the common difference. If I look at consecutive, I'm not stuttering here, I'm telling you consecutive terms, you will find the common difference. What if you don't have consecutive terms? Maybe somebody's being tricky and they want to give you the first term and the fifth term. Well, that's not a problem. If you know the first term is 3 and you know the fifth term is 15, you can still find what the difference between consecutive terms is, because you know the difference between the fifth term and the first term occurred over a span of 4 terms, which means the difference between consecutive terms is 3, just like we set up here. Okay, so to get from the first term to the fifth term, we need to add that difference 4 times. So you had to do that 4 times to get from the fifth to the first. So you're going to take your total difference divided by the span of differences that's being added. It's almost like the change in y over the change in x. But in this case, it's the change in term value divided by the change in term number. So very similar here in regard to slope is our difference. Okay, so common difference is the key for arithmetic. They are linear in nature. The second one is the geometric. And geometric, as I mentioned, is very similar to an exponential. Okay, the key in geometric is that they deal with a common ratio. If you think about our exponential functions, we're talking about multipliers. You're multiplying by something. Well, ratio is division. In order to find that ratio of how you got from one term to the next, you're going to undo the multiplication and you're going to divide. So let's look at this example here. Let's go with 3, 9, 27, 81, and 243. Well, this ratio, the multiplier, is 3. You know, it's kind of weird they call it a ratio because I'm clearly not dividing by 3 here. I'm multiplying by 3. But look about how I got that. My ratio consists of all these terms. Well, my sequence consists of these terms. T1, again, the notation. T2, T3, T4, and T5. So again, if I'm looking at consecutive terms, I can clearly see that from the second term to the first term, I got there by multiplying by 3. From the from the second term to the third term, again, multiplying by 3. 81, the fourth term divided by the third term, is 3. Notice what I'm doing here, though, is I'm taking the later term and dividing it by the preceding term, because I want to figure out how I got there. Similarly to in our arithmetic, we took the later term and subtracted the earlier term to figure out how I got there and have a difference. Even though I added things to get there, I had a difference because I'm undoing it. Here I multiplied, so I'm dividing to figure out how I got there. Division will undo the multiplication. So we can confirm our ratio here is 3 in each of these cases. Now again, what if that guy's being tricky and they didn't give you consecutive terms? Maybe they gave you the first term and the fourth term. Well, we're still smart enough. We know that the ratio occurred 3 times from the fourth to the first, and that the total ratio from the fourth to the first term is 27. And we know the cubed root of 27 is 3. So again, we can figure it out. Okay, it's just like our exponential equations. How many multipliers were there? How many ratios? In this case, there were 3 ratios to go from 3 to 81. Okay, so those 3 ratios total 27, so each individual ratio is 3. Okay, and that is the definition of our arithmetic and geometric sequences. Let's get into some formulas and how we can find equations for these guys. So an arithmetic sequence, again, is very similar to linear. Little different terminology. T sub n is going to be equal to the first term, t sub 1, plus the difference n minus 1 times. Okay, what that means, if you want to find the 10th term, you need to start with the first term and add something 9 times to go from 1 to 10. 9 more terms, 9 more differences will get you the 10th term. If you start with the 5th term, you only get to the 12th, you have to add that 6 more times. Sorry, I forgot what numbers I said, 5 and 12. You need 6 more to get up to there. Okay, so it's always 1 less than what you would think. And kind of put that in perspective a little bit, I'm going to ask you guys a question, and please answer these in your head or jot them down, for instance. How many numbers are there from 0 to 10? Okay, hopefully you have a number in your head. I'm guessing many of you said 10. Some of you said 11. My next question is, how many numbers are there from 1 to 10? Again, some of you probably said 9, but hopefully you all realized, oh, I see what he's doing. From 1 to 10, that's 10 numbers, even though the difference is 9. 10 minus 1 is 9. Yeah, sure. But from 1 to 10, there's 10 terms. Okay, so it's kind of neat that you have the difference does not match up with the actual amount of terms there are. So in case you're wondering, you're not sure, from 0 to 10, there are 11 numbers. And from 1 to 10, there are 10 numbers. Okay, in this case, it's n plus 1, the difference plus 1. Okay, but we're digressing a little bit here. In arithmetic sequence, you're going to take that first term and add not all of them, but all but one of them to get to the 10th term or the 11th term or the 12th term. And I'll show you what I mean here. So let's say you are given T1 equals 5 and the difference is 3, and you are asked to find the 13th term. Sure, we could go ahead and just say, well, 5, 8, 11. I'm counting my fingers here. You can't see that. 14, 17, 20, so on and so forth until I get to the 13th term. Or I could say, oh, well, duh, the 13th term is going to be the first term plus 12 differences. So that's going to be 5 plus 36, or 41, will be my 13th term. Simply plug it into the formula. Okay, and you can do this formula in your head. 5 plus 12 differences. Hey, 5 plus 36. Okay, I'm good to go. All right, so it works pretty well. Now, let's say hypothetical here. They gave you So a slight alteration to this example. Let's say they gave you the third term, and the third term was 11, and they asked you to find the 13th term. Again, given that the difference is 3. Well, the formula only deals with T1, but you can use your brain. You can use your brain and say the same thing, a very similar form of that formula. Well, the 13th term is going to be the third term plus, how many do we need here? How many differences do we need to go from the third to the 13th? 10 differences gives us 41. Okay, so notice 1 plus 12 gave us 13, 3 plus 10 gives us 13. You needed 13 differences. Okay, even though there's really 14 numbers between here. So, I'm sorry, 10 differences because we already had 3. Okay, so be careful. You know, we needed 12 from 1, we're going to need 10 from 3. If they gave us the fifth term, t sub 5 equals 17. Still looking for that 13th term. And the difference is still 3. Well, you can say the 13th term will be the fifth term plus 8 differences. And again, we continue to get 41 here. Okay, so you're just adding how many differences do I need, right? How many differences do I need? 13 minus 1, I need 12 differences. 13 minus 3, I need 10 differences. 10. There's the 12 is in here, 13 minus 1. 13 minus 5, I need 8 differences. So this formula is not applied directly unless you do have T1, okay? So be careful with that. And we'll have more examples following here shortly. Geometric. The geometric formula is similar in the fact that we have t sub n equals t sub 1, but think about what we're doing now. We're not adding differences, we're not adding a number. We're multiplying by a ratio, and again, n minus 1 comes into play. Okay, so if you have that first term, you want to get to the fifth term, you need 4 more ratios. 4 plus 1 is 5. Okay, if you're the first term, you need to go to the 10th term, you need 9 more ratios. Okay, 9 plus 1 is 10. So let's look at an example here again. Let's again say you're given t sub 1 to be, let's say, 2. And you're told the ratio is, let's say 3. And you want to find t sub 6. So t sub 6, right, my n is 6 in this case. I'm looking for the sixth term, any term, n, any term. In this case, n is 6. So t sub 6 equals my first term times my ratio to the 6 minus 1, or to the fifth, right? So I have 2 times 3 to the fifth. Well, that should look very similar to a, b to the x. This is geometric. So 3 to the fifth, quickly in your heads, guys. 3 to the fifth, 3, 9, 27, 81, 243. So 2 times 243, and we can all double that and get 486 is the sixth term. Okay, and same rules apply if you're given the third term, you need to do r cubed, 3 cubed to go with that. If you're given the fourth term, you need 2 more r's, so r squared. Okay, so you can apply the same principles we did in the arithmetic sequence. But again, these are the formulas dealing with T1, okay, your starting point. The last piece I would like to talk about here today is how the similarities between arithmetics and linears and geometrics and exponentials. Arithmetics to linears, and then we'll follow up with geometrics to exponentials. And they are eerily similar. So an arithmetic, let's take 2, 4, 6, 8. I'm going to change what I'm doing right here. Not really thinking too much. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are our terms. These are our terms. We'll call them n, right? Because n is t sub n, the nth term. And this is t sub n up here. And this is where I want my 2, 4, 6, 8, 10. All right, so let's say my first term is 2. My second term is 4. My third term is 6. My fourth term is 8. And my fifth term is 10. Well, that looks like a linear graph if I'm a kid and I play connect the dots. Okay, the difference though is there is no 1.5 value. There's no 2.5. There's no 3.5. There's term 1, term 2, term 3, term 4. N is an integer. N is an integer, and it's an integer that is greater than 0. Okay? So integers greater than 0 are what we talk about with arithmetic. Now, if this was a line, if this was linear with these same terms, see if I can connect the dots here. My graph would look like that. Linear is continuous, where arithmetic, the sequence itself, is discrete. Okay, discrete is just the points. It's a scatter plot. That's not really scattered because it's all in a linear fashion. Okay, where a line is continuous, there is x can equal 1.5 or 1.7 or 0.2 or negative 3. Integers, we don't have the 0th term or the negative 5th term. We have t1, the first term, t2, the second term, t3, the third term, so on and so forth. Okay, the identical thing is true over here with our geometric. That's clearly not a straight line. Actually, that was a straight line, just wasn't a vertical line. That's better. Did you guys know all lines are straight? Think about it. So geometric. Again, we got our terms, 1, 2, 3, 4, 5. That's going to be enough here for geometric. They grow quickly because they're exponential. And t sub n is my vertical axis. Right? We have n for term numbers, t sub n for the term value. They take over our horizontal and vertical axes. And let's say our first term is 2. Our second term is 4. Starting the same way. Third term is 8. Fourth term is 16. So you can see this is kind of growing a little bit here. You can't really see it too well with my graph, but trust me, it is. So again, n is an integer greater than 0. It's discrete. It's a bunch of dots. But if I then go to connect this, right, it's going to, whoops, I'm getting a little squiggly there. It's going to grow exponentially. Okay, so they are similar, but they are not identical. Okay, so there's our difference between arithmetic and linear and geometric and exponential. And let me see if I can get a little bit nicer of a curve going here. Remember, it crosses at 1. And yeah, that's no better. Tough times drawing here today. All right, so that is arithmetic and geometric sequences for the day. And we'll pick up on this stuff in a little more detail tomorrow. Thanks for joining us.